Thousands of years ago, anchors were nothing more than heavy stones or wooden logs filled with lead. Picture ancient Phoenician traders, Greek merchants, and Norse explorers. They all understood one fundamental principle: weight equals stability. Drop something heavy enough into the water, and friction between that mass and the seafloor would resist the pull of current and wind. It was crude, but it worked for small wooden vessels navigating shallow coastal waters. These primitive anchors didn't bite the ocean floor in any sophisticated way. They didn't grip or dig. They just relied on sheer mass and the friction generated between their surface and the sand or mud beneath them. A ship's survival depended entirely on how heavy the anchor was relative to how hard the sea was pushing. It was an arms race. Bigger ship meant heavier anchor. Stronger storm meant needing an even heavier anchor. There was a ceiling to how much weight could be lifted aboard a wooden ship, and sailors frequently found themselves at that limit. But as ships grew larger and trade routes extended into deeper, more treacherous waters, sailors realized something profound. Mass alone wasn't enough. A 50-ton anchor sitting on the bottom provided only marginally more holding power than a 40-ton anchor. The returns were diminishing. Fishermen and sea captains, through centuries of trial and error, understood they needed a new approach. So they forged new shapes: iron hooks, curved flukes, and articulated arms, designs that were engineered not to drag passively across the bottom, but to dig actively into it. These weren't random inventions. They represented a fundamental shift in thinking, from resisting force through weight to resisting force through geometry and design. The anchor's shape became as important as its mass. A well-designed anchor with half the weight of an old stone anchor could now hold twice as effectively. By the Industrial Revolution, everything changed. Ships had evolved into steel leviathans with greater draft, longer hulls, and exponentially more cargo. Traditional anchors simply couldn't keep pace with the demands of these massive new vessels. The technology had to leap forward, and it did. The Stockless anchor was born, a revolutionary design that would dominate maritime technology for the next 2 centuries and beyond. Unlike older anchors with rigid stocks, the horizontal bar that kept the flukes oriented, the Stockless anchor featured 2 pivoting flukes cast as one solid piece of iron or steel. These flukes could rotate and adjust independently, allowing the anchor to orient itself naturally to the seafloor conditions. Drop it into mud, and it would angle itself to maximize penetration. Hit rocky bottom, and it could shift to find purchase in crevices or wedge itself between stones. It wasn't brute force anymore, not in the old sense. A Stockless anchor didn't win through sheer weight. Instead, it won through intelligence embedded in its physical form. The curved, scooped design of the flukes meant that as the chain pulled horizontally on the anchor, the flukes would be forced deeper and deeper into the mud or clay, almost like a shovel digging into earth. The harder you pulled, the deeper it dug. The deeper it dug, the more resistance built up. It was a self-reinforcing system. This was physics itself being used as leverage. When you understand how forces distribute through an object, how shapes interact with different materials, how friction and suction work together, you can design an anchor that grows stronger the more it's tested. You can create a tool where a 15-ton anchor can hold back a 100,000-ton ship, not because the anchor weighs more, but because the physics is perfectly aligned against any force trying to move it. Engineers and maritime designers studied the seabed like never before. They tested anchor designs in controlled conditions, measured holding power, calculated stress ratios. They learned that a muddy bottom could provide suction that increased holding power exponentially. They discovered that in sandy bottoms, the shape of the fluke mattered as more than ever. It had to cut through sand efficiently and then expand slightly to create maximum resistance to being pulled free. The Stockless anchor became the foundation for modern maritime safety. It represented humanity's growing mastery over nature, not through domination, but through understanding. By the time the 20th century arrived, ship captains could venture into any ocean, in any depth, in almost any weather, knowing that physics itself, encoded in the elegant shape of a single piece of cast steel, would keep them safe. Every modern anchor you see today, whether on a fishing vessel or a massive container ship, is a descendant of that Industrial Revolution breakthrough. The technology has refined and evolved, with materials becoming stronger and designs becoming more optimized. But the fundamental insight remains unchanged. The best anchor doesn't win through raw power. It wins because it understands how to transform the forces working against it into forces that bind it deeper to the earth below.